Okay, so optimal trade-offs. So what I'm going to do now is to assume that I have infinite data, infinite computational power. And so what I'll do is to try to find the minimizer of both of these risks, the adversarial risk and the standard risk, for different models. And I would study these for different models and see what kind of trade-offs do I get. Okay, so in other words, what I'm doing is the following. I go over all the possible models theta. Okay, any theta in RP would be one model that I use. For every model, I would basically put the corresponding pair, the standard risk and the adversarial risk computed from that model in this two-dimensional plane. Okay, so that would give me a region of all the possible pairs that I can achieve with using a specific model. Now, for regression, it turns out that this region would be a convex region. Okay. Now, in order to understand trade-offs, we need to understand, we need to study the boundary of this region. So these are the so-called Pareto optimal points of this region. And these are points that, so every point at the boundary has this property that if you fixed one coordinate and try to decrease the other coordinate, you would fall out of the region. Okay, so in other words, these points at the boundary are somehow the optimal points that give us the trade-off between the standard and the adversarial risk. Okay, so we cannot do really better than the points at the boundary. Okay, no matter what our model is. Now let's try to study how this boundary looks for the linear regression problem. As I said, this is a convex region, the region of all these pairs. So in order to study the Pareto from the boundary of this region, we can just use support planes, tangent support planes. This is like a standard trick to study the boundary. So if you look at the objective at the bottom, you want to minimize, given a fixed value of lambda, you want to minimize over the choice of the theta. And by varying lambda, you would basically sweep the boundary of this region. Okay, so this, you can compute this theta of lambda for different values of lambda for any basically linear regression problem. You can obtain closed form solutions. I mean, this is involved. This is like a few pages of calculation. However, what's important is that in the end, you can compute exactly the boundary of this region. And as you see, there is the boundary would be a non-trivial, would give you a non-trivial trade-off between adversarial risk and a standard risk. Let me again repeat that. This trade-off has been obtained with unlimited computational power and infinite data. So in other words, this curve that you see here is the best, okay, absolute best that we can do. And you see there is a trade-off between adversarial and standard risk. If you want to decrease the adversarial risk, you would definitely increase the standard risk and vice versa. Okay, so there is no point that gives you the optimal, smallest standard risk and at the same time the smallest adversarial risk. There is a trade-off. You have to pay a price. So this was about optimal trade-offs. The next question that we want to ask is what happens algorithmically? And as I mentioned before, one class of algorithms that we will consider is the class of algorithms that try to solve the robust ERM problem. Okay, so this is the robust ERM problem. In in the linear regression version, this would be just the quadratic laws applied to the model. Okay, so as you see here. Okay, and remember, theta hat of epsilon would be the solution of the robust ERM problem, where epsilon would be the power of the adversary. All right, so remember the setting of linear regression, everything Gaussian for simplicity right now. N would be the number of data points, sample size, P is the number of parameters. Okay, so the dimension of the input also is in this specific case. So the regime that we want to study these algorithmic solutions, mainly the solution of robust ERM, would be the following regime. We assume that N is large. However, the ratio between N and P is fixed. So that's typically called the overparameterization parameter, delta, as you see. And we want to study how the algorithms, basically how this algorithmic solution behaves with respect to, let's say, different values of delta and so on. Okay, so the main theorem is as follows. So we can, in terms of delta and epsilon, we can precisely compute both standard and adversarial risks. Now the computation comes from, so there are parameters involved in these computations in this formula. These parameters are found used by solving a very simple, like 5-dimensional optimization problem involving simple scalar variables. So this can be solved numerically. And what this in the end would give us this exact value of adversarial risk and standard risk when we do robust ERM for the solution of robust ERM. So the theorem is here. I mean, there is this objective function that you need to solve the minimax problem over. I mean, as I said, it's like a 5-dimensional objective function. It can be done numerically. So what's important is the implications of this theorem that I'm going to study now. Okay, so the exact details are not really important. I'll talk about them. I'll be happy to talk about them offline. So the first conclusion here is algorithmic trade-offs. So as I said, there was this parameter delta, which was the ratio of the number of data points to the number of parameters. So if data is very large, this means that you basically have infinitely many data points compared to the number of parameters in your model. Now, as you see, so here the black curve at the bottom is the optimal curve, is the fundamental limit. As you see, when we increase delta, the curves would converge to the optimal point. So here the conclusion is that as delta grows, as the number of data points grows, adversarial training, the robust ERM, the solution of robust ERM would give us this fundamental trade-off. So algorithmically, we can achieve this fundamental trade-offs provided that this overparameterization parameter would increase. Okay, so the ratio of data points with respect to the number of parameters in the problem. So that's one consequence. The other consequence is exactly the role of this overparameterization delta. Now, as you see here, I'm plotting the standard risk versus the adversary's power epsilon for different values of delta. Here, delta is less than 1. So the problem is underparameterized. And so, sorry, the problem is overparameterized. So you have more parameters than your data points. And as you see, when epsilon is small, the standard risk decreases. Okay, so this means that when epsilon is very small, adversarial training is somehow behaving as a regularizer to your problem. And when epsilon increases, of course, so the adversary becomes more and more dominant, and the standard accuracy, so the trade-offs basically kicks in, and the standard accuracy would basically increase. And the same behavior holds when we are in the underparameterized regime. The same type of observations can be made. Another interesting phenomenon that we see here is the double descent phenomenon. So here, if you look at the risk versus 1 over delta, which is P over N, we exactly see this double descent phenomenon where the risk in the beginning goes down, and then it goes up, and then there is this, and then it goes up, and then it goes down. There is this interpolation threshold that you see, and the threshold also varies with the adversary's power epsilon. Okay, so this phenomenon was observed before in standard regression. However, in adversarial regression, it's interesting to see that this type of double descent curves also hold. All right. So
a quick question here. So
sure,
how would I interpret this? I'm trying to understand the double descent here and
right.
the context of the double descent and non-adversarial linear.
All right.
What's the difference here?
Sorry.
So what is the difference here?
So all right. So let's see. Okay, there are 2 points. Given the adversary's power, if you look at for example, the curve in the right, these are the theoretical curve, and the one on the left is just, sorry, the curve on the left is the theoretical curve, the one on the right is just the empirical, so it's the same thing. If you look for epsilon small, epsilon equals 0.1, you see that the risk goes up and then it goes down. Okay, that's exactly similar to the double descent curve that we have in the non-robust regime. Okay, it's exactly the same. Okay, epsilon small is like some kind of regularization. Now, when you increase epsilon, for example, epsilon equals 1, if you look at the curve for epsilon equals 1, the curve goes down and then it goes up. Okay, so this is a different type of double descent curve. Somehow it's an opposite effect of double descent in the standard regression problem.
So overparameterization is not good in this regime when epsilon.
Excellent, excellent. That's a very good point. So, so 1 over yes. So if So overparameterization is when 1 over delta goes to infinity. Okay, so as you see, in this regime, when epsilon is very large, overparameterization is not useful for us. That's the point. Okay, and it even, I mean, if you see the threshold is, I mean, there is a minimum, right? So it's really not good even. That's a very good observation.
So I guess, I mean, in contrast with the non-adversarial setting here, overparameterization can be good or can be bad.
Can be good and can be bad, right? And this is, by the way, I mean, this is a very good point. By the way, this has also been observed in classification, robust classification.
Okay.
There are empirical studies showing that, look, overparameterization won't really help you. So you get overfitting when you overparameterize, basically.
And do we have a theoretical understanding why
for classification, for neural nets, no.
Okay.
For regression, I tell you in a minute why regression. I think regression is always the first step to understand these adversarial examples because of something that I'll mention in the next slide. Actually, for regression, this minimax problem can be like half solved in closed form. That's the good thing. Okay, for classification, there is really no theory, and this is a really interesting problem to pursue.
Okay.
Thank you, Sally.
Okay.
All right. So let me just say the high-level picture of the proof. I don't want to spend a lot of time on this. So the good thing about regression, as I mentioned, is that the inner max for regression can be solved analytically. Again, there is some derivation here that I'm skipping. However, so the inner maximization problem for regression can be solved. This means that you can always find in closed form the worst case point within the L2 bar or in any type of LP bar. Okay, so essentially what happens so one of the attendees mentioned, you get a different loss function, but this loss function is somehow easy to analyze for us in terms of regression. That's why I'm saying that regression for us is always, I think, the first step to understand all these adversarial kind of behaviors. Now, once you do that, of course, I mean, the loss function is easy to handle, but there's a lot of steps to do and so on. So you can analyze this loss function, you can study its different properties. Turns out that there is a tool that we can use to understand this, the asymptotics of adversarial linear regression, and this tool is the Gordon's method or the convex Gaussian minimax theorem that we will use in order to do that. I mean, there is like 20 pages of derivation and so on here, so I'm skipping everything, but that's somehow the high-level picture or the high-level tools that we are using here. All right, so that was about regression. Let's see, I have around, okay, so let's say I have around, like, I guess 10 minutes. I can maybe quickly talk about the second part of the talk, which is about natural variation. And this is a joint work with a student, Alex Roby and George Papas at Penn.
You can, Hamed, we interrupted you a lot, so you can have 15 minutes if you want.
All right, that's good. That's very good. So I think 15 minutes would be great for me. Thank you, Sally. All right. So, let me do a quick recap of what was natural variation all about. So remember, we said that so images that we see in real world settings, in natural settings, would go under different types of natural variation depending on what kind of natural environment are we working in, right? So we talked about snow images, rainy, whatever, different types of natural variation that could be out there. And as I mentioned before, there are two main challenges regarding natural variation that should be addressed. First of all, the main challenge with respect to this natural variation is that we don't really have a mathematical understanding of these natural variations, right? We don't really have a model, analytical model that, for example, takes as input an image in the sunny weather and gives me as output something snowy. Okay, we don't have an analytical model that can explain this. So the first challenge is to mathematically formulate and understand these type of natural variations. And for example, come up with a model that would give us these type of natural variations. Second, once we have the model, so the second question is how do we leverage these models that we obtain in order to devise algorithms that make our learning-based models robust against these type of natural variations. So I'm going to answer these two challenges briefly for the second part of the talk. In the next few slides, I want to give you the high-level picture of how do we even think about modeling natural variation and how do we devise algorithms given the models that we obtain. And then I briefly talk about the epsilons and deltas, basically, the details a little bit. All right, so what's the general picture? So, so the main question, as I said, is to capture or model this impact, the impact of these natural variations. The way we think about it is simply through something that we call a model of natural variation, which is a function g that takes that has two arguments, x and delta. X would be the image, and delta is something that we call the nuisance parameter. So delta is a very low dimensional parameter. So it's, for example, is in R2 or R3, just 2-3 dimensions. And so the way we think about this function is as follows. So if you take the image x with one specific value for the nuisance parameter, this would give you one image, another. So if you use the model, this would create for you one model, one image with some level of natural variation. And if you change the choice of delta, the nuisance parameter, you would get another image, for example, with a different level of natural variation. And the idea is that by basically changing, by varying this parameter delta, we can produce images with different levels of natural variations. This is the high-level way of thinking about these models of natural variations. Of course, I haven't told you yet about the more interesting problem of how we can obtain this model G. That will come in a few minutes. However, this is the way we are thinking. So there's an image, there's a nuisance parameter. By varying the nuisance parameter, the level of natural variation would be changed. And the question, of course, is how to obtain this model, this function G. Okay. Now, so for the moment, let's assume that we have this function G. We have obtained this model G. Let's see how we can use it and what kind of geometric interpretations this model G has. So what I'm trying to do now is to understand the geometry of these natural variations. Okay, so take an input X. This is let's say an image in sunny weather, and assume that we have access to a model of natural variation G. Now, what I'm going to represent here on the left would be something that I call a learned image manifold. This is the manifold of images that I get when I vary delta and I fix X. So this would be the set of all the outputs of the model G when I fix X and I vary delta. Okay, so each point on this manifold on this surface would basically correspond to a different value of the nuisance parameter delta. So this geometric picture should stand in contrast with the epsilon balls in adversarial examples. Remember, in the first part of the talk, we talked about adversarial examples, and the geometry there was very, very simple. It's just a ball around your point, and then you are searching within that ball. Here, the geometry is slightly more complicated and can be explained using this model G, right? So this gives you a manifold when you vary the nuisance parameter delta. That's how we are thinking about the geometry of such naturally varied images. All right, so given this G, once you have this model G, so this is our assumption right now. I'll talk in a minute how to obtain this model G. But if you have it, the problem of training robust models is again another minimax problem. Okay, so let me explain let me say a few words about this minimax problem. Let me consider the inner maximization problem. The inner maximization problem is really the following. So what we do is that we fix an image X, okay, and we go over the manifold that corresponds to X. We search over the manifold for the worst case nuisance parameter that gives me the highest loss. Okay, that's the meaning of this inner maximization. So I go over basically I sweep the manifold, go over all the possible images, and find the one that has the maximum loss with respect to the loss function that I have and with respect to the model. Once I found that that image with the highest loss, so basically, again, as one of the attendees said, you can basically replace this inner maximization problem with basically delta star, which gives you the highest loss, and that's a new loss that you can basically minimize and find the model. Here, W is the parameters, let's say, of the neural network. Find a model that gives you the best performance with respect to this nuisance, the worst case nuisance parameters. Okay, so that's the minimax optimization problem that once we have the model, we will use in order to make train robust models. All right, so let me now say a few words about how we obtain how we actually obtain these models of natural variation. So I'd like to break this class of models of this class of models into two parts. First, the first and the easier part is non-models, and the second would be learned models. The non-models are models that can be obtained or are available a priori. Okay, so this could be, for example, for non-bounded perturbations, the model would be just a translation within the bound, right? So that's very simple. For rotations, for example, so the nuisance parameter could be just the angle, and the model would be just the rotation matrix times your data point, right? Rotation matrix that corresponds to the angle times your data point. Again, this is a very simple model to obtain. Once you have this model, you can just plug it into this minimax problem, and you try to solve for the best robust model that you can have. Okay, so these are models that are given. You know them. You can just easily leverage them to solve your problem. Now, the more interesting question is for natural variation, where we don't really know the model. We cannot obtain it easily. Okay, so what do we do there? The basic approach that we have, and this is the natural approach here, is to learn this model from data. So that's what we're going to do. And here I'm going to explain again a high-level picture of the details of learning a model from data. And this is based on this framework and the successful framework of image-to-image translation networks. The high-level idea would be the following. So you take your, so the model basically does the following. So you take your input, and there is an encoder that decomposes your input into two parts, the semantic part and the nuisance part. The semantic part captures the high-level details in the picture. For example, the sign, the street sign, as well as the scene, and so on. The nuisance part is aimed to capture the natural variation in the image. And then there is a decoder that, when we vary this nuisance parameter, should give us different different images with different natural variations. Okay, so that's basically the encoder and decoder part. So to learn this encoder and decoding operations, we use there are several GANs, like generative models involved here, and these are learned using the data sets that we have, using different data points that we have. So in general, once we learn this model, that would give us the function g of x and delta. Delta would be the nuisance parameter that we can change in order to obtain different images. So again, that's the high-level picture. I'll be happy to talk about the details offline about this, how we learn this kind of models. All right, so once we learn the model, again, as I said, you can leverage it in this minimax optimization problem to obtain robust models. Okay, so but again, let me also mention that solving this minimax problem is itself a challenge, because first of all, it's a non-convex, non-concave function, especially if you have neural nets. So what people usually do is to use alternating optimization methods. And very briefly, we use three types of methods based on zero-order optimization, first-order optimization, and data augmentation to solve this minimax optimization problem. Let me not go over the details in the interest of time. But the longest story short is that we try to solve this minimax problem approximately using alternating optimization methods. All right, so let me also tell you like one or two experimental setups, because I find it very interesting. And like the original paper has 50 pages of experiments. Here I have cherry-picked two, just to explain to you how these models of natural variation are improving robustness significantly. All right, so okay, so that's just a comparison, the baseline and PGD. Let's not worry about these. Our approach is the three algorithms that I mentioned, and we have a variety of data sets that we train on. Okay, so one of the experiments is the following. So remember about the street sign. So we use one data set. Okay, so this is the data set is called German street signs, whatever data set. These are pictures taken in different cities in Germany. So we use this data set to learn models of natural variation. Okay, so you train using these data sets, you learn different models. But then once you learn the model, you just, let's say, throw away the data set and only use the model. Okay, for different like applications that you have. It's like you learn the model and then you use it on your self-driving car. Now, for test time, we have used a completely different data sets, street signs that are, I think, taken in the city of Atlanta. Okay, so we use this model to train robust classifiers that are robust to natural variation. All right, so you learn that it's like a two-stage approach. You first learn the model from some sorts of data in somewhere that you have obtained, but then you would use your model in the wild to train classifiers later on. And so here are the results. So if you look at the two curves that have performance close to 40% are the vanilla of the classifier, the non-robust version, and also PGD, which is one of the algorithms used for robustness right nowadays. And the other curves are different algorithms that we had proposed using the model-based algorithms. And you see there is around 30% of improvement in terms of robustness with respect to these type of natural variations. Again, let me emphasize that you would learn the model from whatever data set that you have offline, okay, throw everything away, and then use the model in later on, okay? It's only the model that you use. There's no data augmentation that you do. You just use the model. Another quick experiment is on ImageNet data, where you basically, you get the ImageNet data and there are data sets that add different types of things in it, snow or brightness and so on. And again, our method would basically have huge improvements on this ImageNet type of data. The challenge in ImageNet is that you have many classes, very large scale experiments that have to be done. And as you see here, still our methods would provide robustness consistently against various challenges in natural out of distribution kind of shifts on data. All right, let me try to stop here. So there, I mean, again, this field of robustness is really, really open. I mean, for information theorists specifically, there's a lot of things to do. And we have some of the brightest minds in information theory that are currently working on various aspects of robustness. So there are like theoretical new algorithms, theoretical guarantees, different applications to medical imaging, library of models, and so on, which are basically future directions that we're going to pursue here. All right, let me stop here. Thank you very much, everyone.
Thanks a lot, Hamed. This was very interesting. So there's someone. Yeah, so I have a quick question about the model, because there are so many ways you can, and you mentioned a manifold. Is that more you're using it as a, in the loose sense, or what are the properties if you want to learn the model on?
Excellent. So that's a very good comment. So we are somehow, I'm using the manifold as a loose sense basically. So it's really, so by this manifold, we haven't explored yet the properties of this manifold and so on. So all I'm trying to say is that the structure is very different from the simple like epsilon balls that people have in mind often when they are thinking about like robustness. Here is like a manifold that you need to learn or capture in order to provide robustness. You have to walk within this manifold to solve your minimax problem.
And what is the, what are the, when you try to learn this manifold, what are the properties? Because you can fit many, I mean, infinite number of, I'm guessing. So I may have missed the information on the slides. I don't know if
that's an excellent point. So so right now, learning this manifold. But this is again another very great question and another open problem actually. If you have better models, your performance is definitely you can solve the minimax problem better, and your performance would be increased, right? So it will all about how you learn perfect models for this problem. Okay. Now we used one, and this I mean, at least for images, this is something that vision people are trying to do right now. So image-to-image translation. So we are using the state-of-the-art tools from vision in order to learn these models, okay? So the way typically that they do it is through this variational kind of autoencoder kind of structures, where you take the image, you try to decompose the image into two parts, the semantic part and the nuisance part. And then by varying the nuisance part, you would basically try to get different like images with different levels of natural variation. Now, the way to learn these is through some like complicated generative models that involve different convolutional layers and so on. this field, I mean, you cannot really come up with like a deep understanding of what these models, like what's happening inside. People have intuitions, but beyond that, for example, we cannot really say that much about the like how the properties of the manifold are and so on.
Okay, so I don't know if someone else has questions. I think we have time, for one question.
I have a quick question.
Right.
So in the first adversarial model you showed, you showed this trade-off between the error between the standard error and then the error after adding the adversary. Do you see the same phenomena with the natural adversarial model?
Excellent. Very good question. Let me see if I have a. So it's less, but we still see it.
Okay.
Let me see if I have a slide. I mean, everything here is experimental right now. Yeah, I may have. Yeah, I mean, I don't have the slide here, but yes, that's a very good question. But the degradation in performance is much less compared to the epsilon the adversarial examples. We see a bit of degradation, like a few % of degradation, but it still exists. Very good question.
Thank you.
So we'll change the loss formula helps. Say in regression, we can use the Huber style loss.
So you mean in regression, will it change or not?
I'm sorry?
So are you asking about regression, the first part of the talk?
Oh yeah, the first.
Right. Yeah. Okay, that's again a very good question. So we didn't explore that, but I expect that. So changing the loss. Okay, let me show you by.
Yeah, I think we are using the quadratic loss here.
Oh, you're talking about the quadratic loss. Okay, so let me tell you something more general here. So right now I'm using this formulation, right?
Yeah.
Do you see my screen?
Yeah, I can.
Right. So we are using this formulation. This is the robust ERM formulation. We are trying to solve things using this formulation. Okay. Now, so your idea was to let's instead of quadratic, just use some other loss. And people have explored this not for regression, for classification, and you see a bit of improvement, not a great improvement. However, you can even think about a different problem. I mean, nobody says this is the way to relax the problem, right? So there is this paper. I mean, it's called Trades. Okay, by so there is Jiantao Jiao, which is an information theorist in the paper. I know him. So it's a well-known paper. It's called Trades. If you search it, you can find it. There, they say they argue that look, I mean, this is not the best way to solve the problem. They add some regularizer with respect to the standard accuracy, and there they see improvements, notable improvements. Okay, so instead of changing the loss function, they also change the objective. So they get very good, notable improvements. You can look at that paper. It's a very good paper to read. Trade.
Thank you.
Hamed, how do you trades?
Yeah, Trades. Jiantao Jiao. I mean, I guess you know him. He was Saki Weissman's student.
Yeah. Okay, good. All right. Well, thanks again, Hamed, for the nice talk, and it generated some interest actually.
All right, very good. Yeah, I mean, thank you for giving me the opportunity to talk.
No problem. Thanks a lot. Thank you, everyone. So we'll see you next time then.
Great. Thanks, everyone.